Now let's see another example in which we have to calculate the definite integral as a limit of sum. So here we are given the function as e raised to x. The lower limit a is 0 and upper limit b is 1, right? Now let us rewrite the formula, that is the integral is given by limit of h into summation of f of a plus rh as r varies from 1 to n, and the limit is taken as n tends to infinity. So that gives us limit n tends to infinity h summation of, now here a is 0, so once again we have f of rh as r varies from 1 to n. So moving on, we have limit n tends to infinity h into summation of, now the function is f of x equal to e raised to x, so f of rh is nothing but e raised to rh, right, as r varies from 1 to n. So moving further, we have limit n tends to infinity h. Now if you observe what this e raised to rh which is being summed up means is that, suppose we give few successive values to r, that is when r is 1 we have e raised to h, right? When we have r as 2 we have e raised to 2h, then we have e raised to 3h, and so on till we have e raised to nh, isn't it? So the summation basically means this sum. Now if you observe, this particular bracketed expression is nothing but the sum of a geometric progression or a GP, isn't it, in which the first term is e raised to h and it is getting successively multiplied by e raised to h only, so therefore the index increases by 1 every time. And we know that the sum of a GP of n terms has a formula, so therefore let us use that formula to write the sum. So its limit n tends to infinity h. Now the formula is that first term into r raised to n, that is the common ratio raised to n, so that gives us e raised to nh minus 1 upon r minus 1, that is e raised to h minus 1 only, isn't it? Now we know that b is equal to a plus nh while calculating the definite integrals. So b is our upper limit, which is 1, and a is the lower limit, that is 0 plus nh. So that gives us nh is nothing but equal to 1, and this we use to substitute in this particular expression. So therefore moving ahead, we have limit n tends to infinity now what do we do is h e raised to h, here we will have nh is nothing but 1, so we have e raised to 1 minus 1 whole upon e raised to h minus 1, okay? Now if you observe, the expression whose limit we have to find contains the variable h, isn't it? So that means if we can change the variable of the limit, it will be helpful for us. So therefore as n tends to infinity, it is equivalent to saying that h tends to 0, isn't it? Because if you recollect the original process of finding out this limit as a sum, as the number of rectangles increase, that is n increases and tends to infinity, the h, which is nothing but the width of each rectangle, that must eventually tend to 0. So therefore limit as n tends to infinity is effectively same as limit as h tends to 0, okay? Now we keep e raised to h separate, then e minus 1 is already a constant. In the denominator we adjust e raised to h minus 1 upon h. So therefore the h which was present in the numerator is taken down as the denominator of denominator, simply because as you can see in the denominator now we have a standard limit. Okay? Therefore now e minus 1 is a constant, so if we want we can take it outside the limit calculation. So we have the limit of e raised to h upon e raised to h minus 1 upon h as h tends to 0. Now as h tends to 0, this e raised to h will tend to e raised to 0, which is 1, and the limit of the denominator is a standard limit, and that is also equal to 1. So therefore finally our answer is e minus 1. So that's the value of this particular definite integral.